Hello and welcome. Today we're going to take a look at Leetcode 79, word search. Given an n times n grid of characters board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. Right, so neighbors are horizontal and vertical, but not diagonal. And then we have this word here, A, B, C, C, E, D, and we have the board, A, B, C, E, S, F, C, S, A, D, E, E. And we can see here in orange color the highlighted nodes in the board that correspond to the word that we have. So in this case we would return true because the word is in our board. Then we have a second example, again the same letters, but we have a different word, C. So here you can see in orange the highlighted cells that correspond to the word. And then we have a third example where we do not find the word ABCB in the board. So the word is simply not there. Okay, so let's take a look at the drawing to better understand what's going on. So here I have the first example with the word A, B, C, C, E, D, and you can see it's highlighted in red here, and I've also put in the indices under the letters. And that's because to start with we are going to iterate the board, and the way we do that is with two for loops, right? No surprise there. So for I and for j in terms of the board size, rows and columns, and then we get the first element, in this case A. Say A is the first element, and we check is A equal to, we mark it as visited because it's going to be first, and we backtrack if the solution is not found. So, and if we backtrack we remove it from the visited array, but we put it in the visited array, and then we check is A equal to word of 0, and if A is equal to word of 0, then it means that this is valid because it corresponds to the first letter in our word, and then we can continue searching in depth. So we're going to use depth for search, and we're going to get the neighbors of A. So in this case we have B and S, horizontal and vertical neighbors. So let's say we first take node S. We will not mark it as visited because S is not equal to word of 1. It has to be equal to the second element, which is B. So in this case we select node B, the only other remaining neighbor, and we check is B equal to word of 1, and yes it is, and then we mark it as visited. Okay, and then for the next item again we check the neighbors of B. So we have here neighbor C, we have neighbor F, and we have neighbor A. However, A has already been visited, it's already marked, so nothing will happen for this node anymore, or we will not go back unless this solution is not valid. And then we can check node F or cell F, and checking this cell we see that it's not equal to the next element, it's expecting a C. So then we go to the next neighbor C, and sure enough C is going to be equal to word of 2. So C is going to be equal to word of 2, and we put C in the visited list, and then I'll just highlight it here. And again, C has 3 neighbors, B, C, and E, and we will take the other C as the valid neighbor because the other B has already been visited and E is not valid, and C is going to be equal again to word of 3. Okay, and then we have in cell C we have neighbors F, S, E, and C. So we have 4 neighbors this time, and this is how many neighbors we would have normally for all of the cells that are not in the corners, right? So here we have 4 cells, but we have already visited one of them. We've already visited the top C neighbor, so that only means we only have 3 unvisited cells. So we have F, S, and E. So we check if F corresponds to our word, it doesn't. If S corresponds to our word, it doesn't. And if E corresponds to our word, and it does. So we circle E, and E is equal to word of 4, and then again we're going to check the neighbors. Neighbor C is going to be visited already, the top neighbor. Then we can go left and check D, and D is going to be in the list, in the word. D is word of 5. So we have 6 letters, and we are now at the end. We have found all the letters, so that's going to be our condition. So this index here is going to be, we have an index IDX, and if this is going to be equal to word dot size, then so if the length of the word is going to be equal to the index, then we're finished. We found the word and we return true. Otherwise we return false if this condition never triggers. All right, so let's go to the code and let's see how this looks like. Okay, so we are back in Leetcode, so let's code this up. First we're going to need our visited array. I'll call this visited, and we're going to need a vector of directions. So this is for those 4 directions that we are going to go into: left, right, up, and down. Okay, and then okay, if the board is empty, we don't have a match. And otherwise we have board size, and in M is board 0 size, so we iterate the rows and the columns. And we have to initialize our visited vector as well. Okay, and then we return false here. Let's see. Vector bool. Yeah, now it works. So we have our vector initialized. I mean, it compiles. Okay, and then here we say visited of ij is true, and then we backtrack after. Ij is false, and between those two we check if board of ij equals word 0. Then we need our new DFS function here, so we don't have any function yet. DFS, and this is going to take in the board, the I and j index, and it's going to take another index for the word index. Let's call this idx. And here we call DFS of board ij0 0, return true. Okay, and then here we will need a function to get our neighbors, so I'm going to create that. So for each direction I will have a new I plus the first element of the direction, and a new j plus the second element. Okay, then if an I is greater than 0, we want to check the bounds here. Bounds check. And if we have a visited node ni and the cell ni and j, then we push it back to our neighbors. List. Okay. So now we have a way to obtain our neighbors for the current cell. So we can just say neighbors get neighbors of I and j, and for each neighbor and if then we mark it as visited. If the element, the new element, is equals to the word index plus 1. Oops, wrong subscript here. Okay, then visited of n is true. Then we visit this node, otherwise we backtrack. Here we check if DFS of board and I and first and second and index plus 1 return true, right, and otherwise we return false. Okay, so we get the neighbors, we go through each neighbor, we check if the neighbor is the next element in the word, the next character in the word. If it is, we mark it as visited. We continue in depth, and we return true if it's valid, and otherwise we backtrack, we set the visited back to false. And for the get neighbors, we just iterated all the 4 directions, which are in dirs as we defined them in the beginning, and we computed the valid neighbors which were not visited before, and we put them in this array. And yeah, I think this looks good. Let's see. Oh, I need the word as well. In the DFS function, we need to pass in the word. Oh, I forgot the most important part, the terminating condition. So if the index is going to be equal to word size, we return true. Word size -1. Okay, so I forgot here to put the size of the columns m for the Boolean vector, so it was not the correct size. And then we have to have the ending condition here, so if the index is word size -1, then return true. And I think in the diagram I've said it's word size, but it should be -1 because it's an index, right? So it's going to be, in that case, in the case of A, B, C, C, D, it's going to be going from 0 to 5. And if we have 5, we know that we are at the last position and we return true. Okay, so that's it in terms of time complexity and space complexity. Well, let's see if this works first of all. But okay, so space complexity is easy, right? It's O(n) times m. It's in the size of the grid, size of the board, and time complexity is going to be O(n) times m times, and then is going to be 3 to the power L, where L is the length of the word, and three-way we have a three-way recursive tree due to backtracking, And normally it would be four directions, but we never go back to the direction that we came from, right? So we always visit that node and we never go back. So maximum we will have three nodes to visit. So if we take element C here, we come from the C from above, and we no longer go up, and we just go to F, S, and E. So we only have three directions that we go to, and usually with backtracking you have such a time complexity. If you have 3 or 4 or x directions, it's x to the power of the size of the problem space. In this case is going to be the length of the word. Okay, and let's see if it's accepted or not. Yes, it's accepted. Okay, so we can also see the complexity here. It's n times 3 to the power L. Okay, so I hope you enjoyed the video and it was helpful. If yes, you can like and subscribe, and I will post more such solutions, so stay tuned for more C++ Leetcode solutions. Thank you and bye.